This project visualizes navigation patterns from a Turtlebot 3 trained using deep reinforcement learning. The robot learns to navigate autonomously through this environment, avoiding obstacles while reaching randomly placed goals. As you can see, the robot moves continuously forward, adjusting its heading to navigate around walls and toward targets. Over thousands of training episodes, distinct movement patterns emerge. To analyze these patterns, I created a 3D directional heat map that aggregates position and movement data from the training process. Each sphere represents a grid cell in the environment. The size indicates visit frequency, how often the robot passed through that location. As you can see, there is a very large sphere at 0, 0. This is because each time the robot fails to reach its target and instead hits a wall or an obstacle, it resets to the origin for a new run. This also happened so often that I had to create these spheres on a logarithmic scale instead of a linear scale, else everything appeared near the bottom while the 0, 0 appeared very high. The colors encode direction using HSV color mapping. Red indicates northward movement, green shows southward travel, cyan represents eastward motion, and blue or magenta shows westward movement. Directions at each cell are averaged using circular mean, which properly handles angular wraparound, essential when averaging compass directions that might span across 0 degrees. Looking at the visualization, we can identify the learned navigation strategy. Notice the consistent colors in these corridors. The robot has learned preferred pathways. Color transitions show where the robot makes navigation decisions. Areas with high density indicate bottlenecks or frequently visited locations, possibly near common goal positions. The color patterns reveal how the robot approaches obstacles and navigates through narrow passages. The visualization is fully interactive. We can rotate to examine patterns from any angle, revealing three-dimensional structure that wouldn't be apparent from a top-down view. The opacity slider allows us to see through the heat map to the underlying environment map, helping correlate movement patterns with physical obstacles and open spaces. By adjusting opacity, we can see exactly where walls constrain movement and where the robot has learned to exploit open corridors. The visualization technique provides insight into learned autonomous navigation behaviors, revealing both successful strategies and areas where the agent may have developed suboptimal patterns. The heat map serves as both an analysis tool for improving training and a communication tool for understanding what the robot has learned.